table describing all the elements of nature. But have you ever wondered where all these elements come from? Our best theory tells us that only elementary particles, like quarks and electrons, which together form the building blocks of ordinary matter, were created in the Big Bang. These elementary particles were not bound to each other, but moving freely around. Very shortly after the Big Bang, quarks and gluons combined to form protons and neutrons. Some of these protons and neutrons would collide and form deuterium nuclei, a heavy isotope of hydrogen in the reaction seen here. But since the early universe was full of high energetic gamma rays, deuterium was easily destroyed again. After 3 minutes of the Big Bang, the universe had expanded and cooled enough that the photons no longer carried enough energy to break up deuterium. The universe was now cold enough that hydrogen could fuse into helium in a series of reactions known as the proton-proton chain. The overall process is called nucleosynthesis. Since atomic nuclei are positively charged, they repel each other. Fusion thus requires enough energy to overcome this Coulomb barrier. After 15 minutes, the universe was no longer hot enough to bring nuclei close enough together to fuse them, and so the nucleosynthesis came to a halt. After these first 15 minutes of the history of the universe, 75% of the ordinary matter in the universe was hydrogen nuclei, and approximately the last 25% was helium nuclei. All the heavier elements were formed much later in the stars, where they also continue to be formed. In the inner layers of a star, the conditions for fusion are met. The gravitational attraction inwards towards the center of the star creates the high pressure and temperature necessary for fusion. Since most of the universe consists of hydrogen, stars also mainly consist of hydrogen. All stars, light or heavy, spend the most of their lives fusing hydrogen into helium. The fusion process is exothermic, that is, it releases energy. The released energy creates an outward pressure, which balances the inward pressure from gravity. Without the outward pressure, the star would collapse under its own weight. At some stage, the star will have used up all its fuel, that is, when all the hydrogen in the core has been converted into helium. The time it takes for this to happen depends on the mass of the star. The more massive, the faster the process. The consequence of the halted hydrogen fusion in the core is a contraction of the star. The contraction heats up the inner part of the star, and if the star is massive enough, it ignites a new fusion phase. The helium ashes of the hydrogen fusion are now fused into carbon and oxygen, and a new hydrostatic equilibrium is reached between the inward and outward pressures that keep the star together. The difference between a moderately low mass star and a high mass star is seen after the helium fusion phase, where a low mass star ends its life as a core consisting primarily of carbon and oxygen. A heavy star enters a new fusion phase. A very massive star produces all the elements up to iron hydrostatically. In every stage, the product nuclei of the former fusion stage are fused into heavier nuclei, and the core gets hotter and hotter. Around the core are layers of concentric fusing shells. The heavy elements are formed near the center, the lighter elements formed closer to the surface in an onion-like structure. From the chart of binding energies, we see that the energy released per nucleon in a fusion reaction decreases with the increasing number of nucleons in the nucleus. From the chart of binding energies, we also see that iron is the most stable nucleus, meaning that the production of elements heavier than iron consumes energy instead of releasing energy. For a star weighing 25 solar masses, the iron core forms in only one day. This day is the last day of the star's life. Without fusion reactions taking place in the core contracts very rapidly, that is, in less than a second, and the core heats up tremendously, to 5 billion kelvins. During this rapid contraction, the core becomes so dense that the electrons are forced to join with the protons, by which neutrons and neutrinos are produced. Only a few fractions of a second after the core collapse began, the core has been compressed into a very dense sphere of neutrons, packed at nuclear density. That is, the density by which protons and neutrons are packed inside nuclei. It is almost impossible to compress matter beyond the nuclear density. So what happens in the next split second is that matter falling down onto the dense core bounces off it. The process can be compared to you dropping a tennis ball from a height and the ball bounces upwards when it hits the ground. The matter that bounces off the core creates a powerful outgoing pressure wave that in part is pushed forward by the immense number of neutrinos that were created in the core collapse. The shock wave sweeps through the entire star and eventually blows it apart when the wave reaches the surface of the dying star. The star has become a core collapse supernovae. As the shock wave travels through the star, it compresses the material so much that it triggers a new wave of fusion reactions. The tremendous amount of energy released during the supernova fuels the nucleosynthesis of elements heavier than iron. In addition to these fusion reactions, heavier elements are also formed by the bombardment of nuclei by free neutrons formed in the core during collapse. Some of the free neutrons are catched by the nuclei in a process known as the R process, and neutron-rich isotopes are formed. The unstable heavy isotopes can beta decay. That is, a neutron can decay into a proton and emit an electron and an electron antineutrino. In this way, elements of high atomic numbers are formed. Almost all the heavy elements in the universe are believed to be formed in supernova explosions of very massive stars. These heavy stars only account for 0.8% of stars, but 17% of the stars by mass. These few heavy stars can be compared to the bird phoenix. They live a beautiful life, suffer a violent death, and from their ashes new life arises. Except for hydrogen and some helium, all the atoms the Earth consists of, and everything on Earth, including people and animals, is made up of atoms that formed in stars during their life and death.